Okay, the most important application of constant acceleration equations is objects that are in free fall or projectile motion. So in a way, so this is the most important application. Of the constant acceleration equations. Although, in this topic, we are going to use those same three equations that we used in the last lecture. And so free fall and projectile motion, we're talking about whether objects are just dropped from, someone just turns their hand over and drops it and it's falling down, or we're talking about throwing something up into the air and it goes up first and then comes down. We treat all those things the same. So what does it mean for something to be in free fall or projectile motion? There are two requirements. The first one is that nothing is touching it. Something is not in free fall if it's rolling down a ramp. And the other requirement is a little harder it doesn't have quite as fast and clear a rule, but it's that air resistance has a negligible effect on the motion. Okay, so let's think about this. If you have a giant rock and you drop it from 10 feet off the ground, whether you do that in a perfect vacuum or you do that in the regular air, that motion is going to look exactly the same. Whereas now think about an army man with a parachute. If you drop that from 10 feet off the ground, there's going to be a big difference between how that falls without air resistance compared to with air resistance. A parachute is really designed to create air resistance to slow something down. Okay, so we'll talk about what causes air resistance, what to think about in determining whether this is a good treatment of an object for a calculation pretty soon. But for now, let's just say, okay, we're in free fall or projectile motion. Then what can we say about the motion? So if these conditions are met, then everything always, so whether it's on its way up or on its way down, has a downward acceleration of 9.8 meters per second squared. So if these conditions for free fall or projectile motion are met and nothing's touching the object and the air resistance has a negligible effect on the motion, then you always know the acceleration going into your calculation. Okay, well, let's think about, I said I introduced this as free fall or projectile motion. So you can think of like free fall, the thing is always moving down. Okay. Projectile motion, you can think of at the start at least it's moving up. So what about the acceleration in those two different cases? The answer is whether it's going up or going down, the acceleration is always down at 9.8 meters per second squared. And you can make sense out of that if you think of, so let's just talk about this intuitively. On the way up, what happens when you launch an object up into the air until it reaches the highest point? It's slowing down the whole time. It's just slowing down steadily until it gets to the highest point. And so let's think about the direction of the velocity. If it's on the way up, the velocity is up. Usually we call, I'm going to always consider up to be positive, so we could say it at a positive velocity, but we can also just draw arrows in the direction. So the velocity is up. The thing is slowing down until it reaches its highest point. So what does that tell you about the direction of the acceleration when a thing is on its way up? If something is slowing down, we know that the velocity and acceleration are in opposite directions. So that tells you that the acceleration has to be down when the thing is on the way up. Okay? Now let's think about when it's on the way down. Now the velocity is down. Usually for us, we would make our positive direction up, and so that would be a negative velocity, but you can just draw the arrow. And what's happening to the object on its way? Well, you know that right when you first drop it, it's going very slowly. It speeds up as it goes down. So if it's speeding up and the velocity is down, the acceleration also has to be down. So what this is saying is whether it's on the way up, on the way down, that acceleration is just steadily down the whole time. That doesn't tell you what the magnitude is, but I think you can believe me at least that the magnitude of the acceleration is always 9.81 meters per second squared, pointing down. Okay. And so now I want to introduce the first common misconception in this class. So in this class, you have intuition about all of these things we're talking about. This is all stuff you've seen and done before, things flying around, rolling, that kind of stuff. And usually that's helpful in this class, but there are 4 places in this class where it's not helpful because for almost everybody, their intuition about this stuff is wrong. And so not only do you have to learn the right way, but you have to sort of consciously undo the thing in your brain that's telling you the wrong stuff. So, okay, common misconception number 1. Common misconception number 1. And that is, this is what most people tend to think intuitively. Doesn't gravity make heavier things fall faster? So in that case, you can picture like a big rock being dropped at the same time as let's say a feather. That's going to come up in a second. Your intuition says that, okay, the rock is going to fall faster. The feather is going to take longer to hit the ground. And you kind of have this natural connection between the weight of the object and how fast it falls. And the truth is, you're not crazy. A rock will fall faster than a feather, but it doesn't have anything to do with the natural result of gravity. The only thing when things like this do happen, where a big rock falls to the ground faster than a feather, it doesn't have anything to do with the effect of gravity. It just has to do with the effect of air resistance. So when that happens, it's only because of air resistance. Okay, well, we said that in order to use this treatment of objects as being in free fall, projectile motion, we have to be able to neglect the air resistance. The air resistance has to be small compared to its motion. And so we're not considering air resistance here. And so if you get rid of the air resistance, this giant rock and this feather will fall exactly the same. If you want to be a little more morbid about it, a giant rock, a feather, and a helicopter would all find the same fall at the same rate, because the way a helicopter moves just has to do with its rotors creating a reaction with the air around it. Okay, so this is something you have to remember. Heavy things don't fall faster unless air resistance has a different effect on, the other thing. And so I'm here going to start a video that shows, it's a really cool video. They're going to go into this aerospace testing facility where they're able to actually pump air out of a giant building, and then they can do these experiments with multiple things in free fall. And they're going to drop a bowling ball and a feather at the same time. And before they pull the air out, they fall exactly the same you would expect. The bowling ball smashes to the ground, the feather slowly flutters to the ground. But once they pump all the air out of the building, it's amazing to watch. These things just fall exactly the same. So I'm giving away the punchline, but I want you to know what to look for. Okay, so here is the video.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down.
Okay, so yeah, pretty interesting. I really, what I do wish is that they would have shown it in just real time instead of only showing it in slow motion like that. But yeah, what you can see is the difference in the way a light thing falls and a heavy thing falls doesn't have anything to do with gravity. If there's no air resistance, they have the exact same acceleration. So the next question then, I guess, that naturally comes up is, you know, when then is air resistance important? So this is where the video was. So when is air resistance significant? Because in those cases, we can't use this free fall approximation. So air resistance has a bigger effect. The effect increases as first, the weight of the object goes down. Okay, so you know, I said in the common misconception, like gravity doesn't make heavy things fall faster, but it is one of the things that determines the effect of air resistance, and that's why our intuition is wrong about the way gravity acts on different things. The second thing that's important is as the surface area goes up, the air resistance effect increases. So in this case, you can think of like a parachute. A parachute is designed to have a very big surface area, and that's what allows it to create all this air resistance that slows a falling object down. And the last thing, and the one that has the biggest effect, is an object's speed. So a thing that's moving, so the air resistance effect increases as the speed increases. As the speed increases, there's a very big increase in the force that air resistance applies to things. That's why if you are thinking about like, let's say, well, let's think of animals that move at different speeds. A snail or a turtle, their bodies aren't aerodynamic in the least because they move at very slow speeds. There's no reason for it, no matter how their body's shaped, they're going to be able to move freely without worrying about air resistance. But now think about things like peregrine falcons or animals that move very fast. Their bodies are very streamlined in order to decrease air resistance as much as possible. And that's because the faster you go, there's this big increase in air resistance. Okay, the one last thing I want to say before we start getting into calculations involving free fall and projectile motion. So these are two important facts that we'll use in calculations. The first one is if an object is dropped, okay, rather than thrown or launched or whatever, if an object is dropped, then its starting velocity is the same as the velocity of whatever it's dropped from. So if it's dropped from an elevator that's moving up at a certain speed, at the instant it's released, its velocity is going to be the velocity of the elevator. Once we start doing stuff in 2 dimensions, that'll be true for a car or an airplane or a helicopter or whatever too. But so if an object is dropped, then its starting velocity is the same as what it's dropped from. Well, that also works if it's dropped from the ground or from a bridge or from the window of a building. All of those things are at rest. They have 0 velocity. And that means that at the instant you drop something from those things, the velocity of the object is 0. The second fact that we're going to use is that if an object is launched up or thrown up, it reaches its highest point when its velocity is 0. And we're going to use that fact in any problem where it mentions something at its highest point, asks you for how high the thing is at its highest point. We're always going to use this fact. That happens when the velocity is 0. So other than knowing the acceleration of something that's in free fall or projectile motion, and knowing these 2 facts, the process for doing free fall and projectile motion problems is going to be exactly the same as any other constant acceleration equation. And the next video you're going to see is just examples of doing calculations involving free fall and projectile motion.